This video uses the one sample z-test as a way of introducing the concept and calculation of interval estimation and confidence intervals. In the previous video, we used the mean SAT score from a sample of 64 students who received our math intervention as an estimate of the theoretical population average for all students who may ever receive our intervention. Notice that this is a very specific estimate. We're saying that we think that population average mu is exactly equal to 530. This is called, not surprisingly, a point estimate. It's a single specific value that estimates whatever population parameter in which we're interested. In this case, our point estimate for the population average mu is our sample average x bar. But we have other point estimates, such as the lowercase s for sigma, the population standard deviation. Now, obviously, the average from our sample, 530, isn't going to be exactly equal to the true population average. That's one of the limitations of a point estimate. The real population average, if we could give our intervention to everyone and measure SAT scores for everyone, maybe around 530, maybe a little higher, maybe a little lower, but somewhere in a range around 530. This is where the idea of an interval estimate comes in. An interval estimate is some range of values within which we have a level of confidence that the true population parameter in which we're interested lies. Conceptually, it's pretty straightforward. In this case, we calculated our sample mean, which is our point estimate of what we think mu is. We just need some measure of variability for how spread out sample means would be if we sampled over and over and over an infinite number of times. But that's what the standard error of the mean does. We can use our observed sample mean and the standard error of the mean to estimate that range. We call this the confidence interval. Now, our sample mean was 530, but again, we know that different samples would be spread out, higher or lower than this. The standard error is that yardstick that tells us how spread out we would expect sample means to be for different samples. We can then use z-scores in the normal curve to tell us the distribution of sample averages that would fall within some given range. For example, we know that 90% of our distribution, in this case our sample means, fall between a z of negative 1.64 and a z of positive 1.64, with 5% of the scores falling below negative 1.64 and 5% falling above positive 1.64. We can think of that positive and negative 1.64 as bounds for 90% of the distribution. They're the fence that contains 90% of the distribution centered around the mean. Similarly, we also know that 95% of the distribution, again in this case we're talking about sample means, falls between a z of negative 1.96 and a z of positive 1.96. So we can think of that positive 1.96 and negative 1.96 as bounds for 95% of the distribution. Now, let's put all of this together into a formula for confidence intervals. First, we'll calculate what's called the 95% confidence interval. It's equal to the sample mean plus or minus the two-tailed z-score that bounds 95% of the distribution times the standard error of the mean. So let's plug in values. Our 95% confidence interval is equal to x bar, or 530, plus or minus our z-score that serves as the bounds for 95% of the distribution, We just saw that this was plus or minus 1.96 times the standard error of the mean, which we calculated in the previous video, was 12.5. We do a little quick math and see that 1.96 times 12.5 is equal to 24.5. We then calculate the lower limit of the confidence interval by subtracting 24.5 from 530, and we calculate the upper limit of the confidence interval by adding 24.5 to 530. This gives us 505.5 and 554.5. The confidence interval is the range of scores between the lower and upper limits. So our confidence interval ranges from 505.5 to 554.5.
Well, isn't that special?
Okay, that's nice, but what does it mean? What does it really tell us? Now, you'll hear people talk about having high confidence or 95% confidence that the population mean is somewhere in that range, or that 95% of the time the population average would fall in that range. But let's take a closer look at technically what exactly the 95% confidence interval tells us. Let's say I obtain one sample, calculate the 95% confidence interval, and it gives me a range reflected in this blue line, with the lower limit to the left and the upper limit on the right. The confidence interval is the entire range of scores along that blue line between these two values. Now, let's not worry about what the actual values are. Just think of this as a range of scores. Different people then go to the same population and get a different sample and calculate a 95% confidence interval for that sample. Notice that it's different from the first because it's a different sample. In this case, it's a little narrower and a little more to the lower end of the distribution. We then get another sample and another sample and another, and so on and so on and so on an infinite number of times. Okay? Let's then say that I somehow magically find out exactly what the true population mean is, and indicate it here with this black line. Now, notice something. See how in most of the samples, the 95% confidence interval that was calculated overlaps or contains that true population mean, which was mu. Now, not always. If we did an infinite number of samples, there would be some cases where the 95% confidence interval based on those samples does not overlap or contain the true population mean. And that leads us to a more technical and accurate description of a 95% confidence interval for the population mean. If you have an infinite number of samples from the same population and calculate a 95% confidence interval for the population mean based on each of these samples, 95% of those 95% confidence intervals would overlap or contain the true population mean. Now remember, I don't actually know what the true population mean, mu, is. In this example, I'm estimating the mean of the population of people who could potentially receive the intervention. We don't know that population average, that's why we're estimating it. And notice that it's not mu that's jumping around. It is what it is. It's the samples that jump around and our estimates based on those samples that fluctuate. But confidence intervals give us a sense or estimate of the range in which we think the actual population mean exists. In a way, you can see that illustrated here. The curve is the sampling distribution of means based on the null hypothesis being true. This reflects the sample means we would expect to see if the null is true and mu, our population average, really is 500. The red lines indicate the critical z-scores we would need to reject the null, and the red shaded area indicates the region of rejection. The dotted blue line indicates the observed mean, while this solid horizontal blue line reflects the 95% confidence interval. Based on the mean and standard error, this is the range where we would expect to see the population average based on our sample mean of 530. Again, the confidence interval reflects the range of values where we believe the mean for our population lies. Remember, the population we're talking about is the population of students who receive our intervention. The fact that this range does not include 500 tells us that the mean for the population of people taking the intervention probably is not 500. In other words, the distribution of means does not look like the curve we've graphed here, which was based on the null hypothesis being true that mu is 500. The real sampling distribution of means for people taking our intervention is probably higher and shifted to the right. This is an important point. Remember, the null hypothesis is that mu is equal to 500. But our confidence interval is telling us that we think mu is somewhere between 505.5 and 554.5. Our null hypothesis value of 500 is outside that range, so the null value of 500 doesn't seem very plausible based on our confidence interval. This gives us an additional insight into the 95% confidence interval when alpha equals 0.05. If the value for the null is in the confidence interval, you'll fail to reject the null. If it's not, you'll reject the null hypothesis. In essence, the 95% confidence interval is also telling you the range of values for which you would fail to reject the null hypothesis when alpha is 0.05. There's an inherent synchrony between a 95% confidence interval and an alpha of 0.05. For example, if instead the null hypothesis was the mean of intervention students is 506, we automatically know that we would have failed to reject the null because 506 is inside our confidence interval. But if the null was instead that the mean of intervention students is equal to 505, we automatically know that we would have rejected the null because 505 is outside our confidence interval. Now, of course, we focused on the 95% confidence interval, but the exact same principles can be applied to calculate a confidence interval for any range of confidence. In addition to a 95% confidence interval, you typically may see a 90% confidence interval or a 99% confidence interval reported. Remember, for the 95% confidence interval, we just take the sample mean plus or minus the z-score that bounds 95% of the normal distribution times the standard error. Therefore, the generic equation for the 95% confidence interval is just x bar plus or minus 1.96 times the standard error. And the 90% confidence interval is just the sample mean plus and minus the z-score that bounds 90% of the normal distribution times the standard error of the mean. Or x bar plus and minus 1.64 times the standard error. Now that synchrony that we noted between a 95% confidence interval and an alpha of 0.05 also exists between a 90% confidence interval and an alpha of 0.10. If the alpha is 0.10 and the 90% confidence interval contains the null value, you'll fail to reject the null. And if alpha is 0.10 and the 90% confidence interval does not contain the null value, you'll reject the null. Okay? Now, to calculate a 99% confidence interval, we need to know the z-score that bounds 99% of the normal distribution. That's the z-score of 2.58 within rounding. So the 99% confidence interval is just the sample mean plus and minus 2.58 times the standard error. And again, we see the same synchrony between the 99% confidence interval and in this case an alpha of 0.01. If alpha is 0.01 and the 99% confidence interval contains the null value, you'll fail to reject the null. On the other hand, if alpha is 0.01 and the 99% confidence interval does not contain the null value, you'll reject the null. What's nice about the confidence intervals and this whole idea of interval estimation is that it gives you a sense of the precision of an estimate. Someone can report a point estimate of what they think the population mean is, and in some cases it may be very precise. We may expect it to be very close to whatever that true value is. On the other hand, at other times, someone may report a point estimate that's not very precise at all. In that case, the confidence interval tells us that while they might predict a specific value, the true value could be all over the place. Confidence intervals tell you how precise an estimate is. Now, while we've been talking about confidence intervals for the population mean, you'll see the same principles used to calculate confidence intervals for other population parameters, such as effect sizes or regression coefficients. And also, while we've introduced this using a one-sample z-test, you'll see confidence intervals used in conjunction with all sorts of statistical tests and procedures. Okay? So this wraps up our discussion of a one-sample z-test, plus our introduction into confidence intervals. Everything all right? Okay. Bye for now.